Pluto, a far-off and befuddling body, was once thought to be a particular and certifiable planet, a singular piece of our planetary family. However, later, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding disclosure. They propose that this cold world is on a potential impact course with Neptune. But how could this happen? Furthermore, what might be the consequences of such a massive event? Are we witnessing an interesting orbital eccentricity, or is there something more to this impending cosmic occurrence? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was relegated to a lesser status, remains a subject of interest and study in the cosmic community. According to persistent calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are sounding the alarm about a potentially catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unusual compared to any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it has not even completed one full revolution. However, the intrigue does not stop there. Pluto's orbit is characterized by its extremely eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more erratic compared to other planets. This inclination and irregularity add layers of complexity to its orbital pattern. Perhaps one of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For approximately 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to explain its unusual trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood apart with its steep inclination and irregular shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This concept deals with understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact with one another through their gravitational forces. It is like trying to predict their movements based on their initial positions and how they pull on each other. For Pluto, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Terms like asymptotic libration, scope libration, and the VZK wobbling are key components of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a type of libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, its position is always about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from interfering with each other. Degree libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this suggests that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection against potential collisions. Another critical factor in this scenario is the VZK wobbling, named after three scientists V, Z, and K, who studied the movement of celestial objects in space. This concept explains how gravitational interactions between three objects, such as Pluto, Neptune, and the Sun, affect their orbits. For Pluto, the VZK wobbling helps us understand why its path near the Sun is so unusual. Despite its apparent irregularity, this effect contributes to stabilizing Pluto's orbit over incredibly long periods. The VZK wobbling illustrates that although space may seem chaotic and unpredictable, specific patterns and forces help maintain order. These factors help regulate Pluto's orbit, ensuring it does not collide with Neptune or veer off course. The three-body problem plays a crucial role in understanding these orbits. particularly how celestial bodies interact gravitationally. Studying this phenomenon allows us to better comprehend Pluto, our neighboring solar system, and even distant stars and exoplanets. Mathematical simulations in the late 1980s revealed that, despite its predictable properties, Pluto's orbit is still highly sensitive to small variations in initial conditions. These variations can lead to vast differences over long timescales. However, these peculiar attributes of Pluto's orbit have been found to maintain consistency over extremely long durations. Recent computer models have helped scientists understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune has a fascinating relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. However, Neptune is not the only factor. Jupiter's gravity also plays a critical role in safeguarding Pluto's trajectory, and Saturn contributes as well. These studies indicate that Jupiter's gravity alone is sufficient to keep Pluto on a stable course for an incredibly long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn work together to ensure Pluto remains safely in its orbit. These orbital peculiarities are vital in the grand scheme of the universe, maintaining the stability and order of celestial bodies. Without these gravitational interactions, our solar system would be far more chaotic. Bodies like Pluto could indeed collide with others or be ejected from their stable orbits, triggering a domino effect on other celestial objects. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This provides a clearer picture of the dynamic nature of planetary systems. The case of Pluto demonstrates how, even in seemingly unstable orbits, equilibrium can be achieved through the intricate interplay of gravitational forces and orbital mechanics. Furthermore, it highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital resonance, which implies the delicate dependence of a celestial body's orbit on its initial conditions, is clearly exhibited in Pluto's case. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term trajectory. Using computational simulations has been crucial in studying Pluto's motion through space. These models employ complex mathematics to simulate how Pluto and other celestial objects, like Neptune, interact gravitationally. By tweaking small details in the simulations, astronomers can see how even minor changes can drastically impact Pluto's eventual path. In the late 1980s, despite the complexities of Pluto's orbit, its long-term stability suggests that our solar system operates under delicate but well-balanced gravitational forces. While Pluto's trajectory may seem chaotic, it follows a predictable pattern over extensive timescales, thanks to the intricate interplay of Neptune, Jupiter, and Saturn's gravitational influences. However, if a significant external force were to disrupt this equilibrium, such as the gravitational pull of an unknown massive object or an unanticipated shift in Neptune's orbit, it could set off a chain reaction, altering Pluto's stable path and potentially increasing the chances of a collision. Could Pluto ever collide with Neptune? Given Pluto's current orbital characteristics and its 2:3 resonance with Neptune, a direct collision is highly unlikely. This resonance ensures that Pluto and Neptune never come dangerously close to each other despite their overlapping orbits. The gravitational interactions between these two bodies, as well as with the other gas giants, create a self-regulating mechanism that maintains order in the system. Nonetheless, long-term simulations suggest that over billions of years, small gravitational perturbations could accumulate, leading to unpredictable outcomes. If, for instance, an external celestial event, such as a passing rogue planet, a close encounter with a massive Kuiper belt object, or an unexpected shift in the Sun's gravitational influence, were to disturb Pluto's delicate balance, it might destabilize its orbit. While such a scenario remains speculative, it underscores the importance of continuously monitoring celestial mechanics and refining our understanding of orbital dynamics. What would happen if Pluto and Neptune collided? If hypothetically Pluto and Neptune were to collide, the impact would be catastrophic on an astronomical scale. Pluto, despite being much smaller than Neptune, possesses enough mass and velocity to create a significant cosmic event. The aftermath of such a collision would likely result in 1. The formation of a new debris field. The impact could scatter fragments across the solar system, potentially creating a new asteroid belt-like structure near Neptune's orbit. Some debris could be ejected into interstellar space, while others might be captured by the Sun or other planets. 2. Changes in Neptune's atmosphere and structure. The immense energy from the impact could alter Neptune's atmospheric composition, potentially causing massive storms or changes in its magnetic field. If the collision were powerful enough, it might even strip away part of Neptune's outer layers. 3. Potential effects on Earth and the solar system. A disruption in Neptune's orbit could have ripple effects on the entire planetary system. If debris from the collision were redirected toward the inner solar system, Earth and other planets might face an increased risk of asteroid impacts. 4. Destabilization of Kuiper belt objects. A major collision could send shockwaves through the Kuiper belt, causing other trans-Neptunian objects to shift or be ejected from their stable positions. Fortunately, current orbital models suggest that such an event is exceedingly unlikely, thanks to the protective mechanisms built into Pluto's orbital resonance. However, the unpredictability of long-term celestial mechanics means that continued observation and refinement of our models remain crucial. The future of Pluto and the importance of space exploration. As humanity advances in space exploration, missions like New Horizons have provided invaluable insights into Pluto's composition, atmosphere, and geology. Future missions could further refine our understanding of Pluto's orbit and its interactions with Neptune and the Kuiper belt. Additionally, advancements in computational modeling will allow astronomers to simulate even more precise long-term predictions regarding planetary movements, helping us prepare for any potential cosmic anomalies. Pluto's unique orbit serves as a fascinating case study in celestial mechanics, demonstrating how even the most erratic-seeming paths can be governed by subtle yet powerful gravitational influences. The study of Pluto not only enriches our understanding of the solar system's past, but also provides critical insights into the stability of planetary systems beyond our own. As we continue to explore the cosmos, Pluto remains a reminder of the dynamic and ever-evolving nature of our universe, a small but significant piece in the grand puzzle of celestial motion. The universe. While we've made huge steps in understanding space, Pluto's model helps us to remember how our comprehension of the universe is still restricted. Understanding the gravitational impacts of the giant planets on Pluto's orbit offers significant insights into the broader dynamics of the nearby solar system. It shows how the presence and position of every planet can have sweeping consequences for the stability and trajectory of different bodies within the system. So, why are prominent astrophysicists suddenly raising concerns about a possible impact between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length perspective on the mysteries of our nearby planetary system, especially the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. His stance on Pluto's reclassification is framed within the ever-expanding knowledge of our planetary system. He sees the reclassification not as a diminishment, but rather as a necessary adjustment in line with our growing understanding of the numerous bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He acknowledges the complexity of Pluto's orbit and its interactions with Neptune from a perspective that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still need to learn about the forces shaping our planetary system. In the grand scheme of things, Pluto's orbit is a fascinating case study in the intricate interplay of gravitational forces within our nearby planetary system. While its orbit is stable right now, the mysterious interactions between Pluto, Neptune, and other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better understand the delicate balance that governs the movements of celestial bodies. The potential for a Pluto-Neptune collision is not necessarily imminent, but it serves as a reminder of the ever-evolving and perplexing nature of the universe. Despite the established theories surrounding Pluto's orbit, it is crucial to consider the broader implications of these dynamics for our understanding of the nearby solar system and the universe at large. While Pluto's journey is one of curiosity, it is also a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a key piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2 to 3, is a fundamental aspect of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that, despite their orbits crossing, the 2 planets never collide. This is a result of gravitational interactions that stabilize their paths, working together to prevent catastrophic impacts. The importance of resonance in maintaining stability cannot be overstated. It provides a remarkable example of how systems in space, even those that initially appear chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its irregular orbit, has remained stable for billions of years. This dynamic is a crucial component of the larger structure of the nearby planetary system. The effects of planets like Jupiter, Saturn, and even Uranus are essential in maintaining the stability of the orbits of smaller bodies like Pluto. Jupiter, with its massive gravitational influence, acts as a kind of guardian for the interplanetary system by affecting the trajectories of various asteroids and dwarf planets, including Pluto. In fact, some scientists speculate that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely. Without Jupiter's protective influence, Pluto's orbit could have been significantly more disrupted, potentially sending it out of the Sun's gravitational reach. While the idea of a Pluto-Neptune collision may seem alarming, it is important to understand that the hypothesis is based on theoretical scenarios rather than immediate danger. Pluto and Neptune's orbits are incredibly complex, governed by delicate resonances and gravitational forces that ensure their paths do not intersect catastrophically. Despite Pluto's highly elliptical orbit, its gravitational dance with Neptune and other giant planets keeps both on stable trajectories. However, astrophysicists like Neil deGrasse Tyson suggest that even the most stable orbits may experience disruptions over unimaginably long time scales. This has raised concerns that small variations in Pluto's orbit could lead to significant changes in its future trajectory, potentially bringing it closer to Neptune. Nonetheless, it is essential to remember that such predictions are based on long-term modeling and simulations, which are still subject to uncertainties due to the chaotic nature of orbital mechanics. The role of Jupiter in stabilizing Pluto's orbit cannot be overstated. Jupiter's immense mass and gravitational pull have a profound influence on the entire solar system, particularly on smaller bodies like Pluto. It acts as a kind of cosmic shield, helping to prevent potential disruptions caused by other celestial bodies or minor variations in Pluto's orbit. Some scientists theorize that without Jupiter's influence, Pluto's orbit could have been even more unstable, leading to an increased likelihood of a collision or even being ejected from the planetary system entirely. This highlights the interconnected nature of the solar system, where the gravitational forces of one planet can significantly impact the behavior of others, even those as distant as Pluto. Moreover, Neptune's gravitational influence on Pluto, although seemingly benign due to orbital resonance, remains a subject of interest for researchers. as Pluto completes 2 orbits around the Sun for every 3 orbits completed by Neptune. Their relationship is finely tuned. The 2 planets' orbits are locked in a stable rhythm, preventing any direct collision. However, even slight shifts in the masses of nearby celestial bodies or the overall structure of the solar system could alter this balance. While current models suggest Pluto's orbit will remain stable for billions of years, the unpredictable nature of space means that new discoveries and insights into planetary dynamics could eventually reveal new forces at play, challenging our understanding of the solar system's stability.